Okay, in this lesson, we're looking at vectors in 3-space. So up until now, you may have actually never even really graphed in 3-space. We always do it in 2-space with just the x and y axes. But in 3-space, we add a z axis. And when you look at these pictures, they look, I think most people think, well, why wouldn't you leave x as horizontal, y as vertical, and z as the one that's on a diagonal compared to the other two? But as a standard, we tend not to. We tend to draw axes like this, x, y, z. That's the typical standard, at least that I've seen. But again, as long as it's labeled, it doesn't have to be. We're gonna look at something in a minute where in this day and age of technology, some of these standards maybe become less relevant. Okay, so we're going to look at some definitions. All of the stuff that we've done so far, adding vectors, multiplying by a scalar, and the dot product, we're going to look at all of them in 3-space. And we're going to start to do some of the kinds of questions that you see that are all mixed up together that start to give us an idea of why this unit can be a bit tricky, because it's all brand new. Everything that we're doing is in just all the way new notation and terminology. And so understanding what questions are asking is part of what makes it difficult. Just understanding. The actual doing it, usually carrying it out, is usually fairly straightforward. But there's all different kinds of questions. And if you don't have a good sense of what the different terminology is and what the question's asking, then you're not going to be able to answer it. So let's come up with a few definitions first of all. And all of this is fairly, I think, intuitively scaled from 2-space to 3-space. You can already see in the general case here, or in specific cases like in example 1, you can see that we just add an extra coordinate. So instead of having 2 coordinates, x and y, we have x, y, z. So if v is a vector in 3-space and it has its tail at the origin, then it's represented by coordinates p, x1, y1, z1. Position vector would be from O to P. So this is a point, right? And this is a vector. So this is the vector from O to P, where P is that point, essentially. So let's sketch a couple. Now this is tricky, and if you're not good at sketching, then this, or not, good visual and that kind of and drawing, and then this is especially difficult. It's not a main focus of this course or of this unit, so we won't overthink it, but it can be an interesting exercise. So we are going to sketch this vector. Now, first of all, I'm going to try to, I think it'll help if I have a decent sort of scale here. Okay, so I'm going to go 1, 2, 3, 4, 5. Doesn't have to be perfect. And 1, 2, 3, 4, whoops. 5, and oops. 1, 2, 3, 4, 5. Okay, so I've got my scale. Now here's what I'm going to do. I'm going to draw a box because it's hard to visualize. I mean, what we're doing is we're trying to represent 3-space, so a point in 3-space or a vector in 3-space, but we're representing it in 2-space. We're representing it on a screen or on a piece of paper. So that's obviously what makes this tricky. So this is 2x, 3y, 4z. So what I'm going to do is I am going to go to 3 on the y-axis, and I'm going to draw out, try to go as parallel as I can to the x-axis so that I can make a box. And if I have to kind of cut it off to keep things even, then that's fine, right? So So I've got a square here that comes from 2 out on the x and 3 out on the y. Then I'm going to go 1, 2, 3, 4 on the z, and I'm going to draw, again, I'm going parallel here to the y-axis and draw down. Okay, and then I'm going to go parallel to the, so this one's going to come up here, and this one's going to go parallel to x. That was a bit too much. Oh, it's better. Okay, and then I'm going to come out and connect everything. And you don't actually have to draw a full box. You don't need every single one of those lines, but it can be helpful. And so now we can see, so if I'm going to just scribble on this first, and then I'm going to erase that. Okay, so I'm starting at the origin, and I'm going 2 on the x, 3 on the y, and then 4 on the z. And that's where I'm finishing at that point there. So this point, and then this is my vector to that point, right? So that's how you can draw sort of vector in 3 space on a piece of paper and sort of visualize it. It's not honestly all that useful, but it can be just kind of, I suppose, fun to see what this feels like. We'll do one more. I'm just going to do this one more quickly. So let's see. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So it's negative 3 in the x. So that's why I went the other direction, obviously. And 1, 2, 3, 4, 5. So I am going negative 3 in the x. 1, 2, 3. 2 in the y. So something like that. And then 4z. So 1, 2, 3, 4. And this is going to come out like this. And down. Across. Down. Okay. And this one's going to come across to about there. Go down. And go like that. So this time, starting here, we're going negative 3. 1, 2, 3. Then 2. Then 4. So I'm going to this space up here, right? There we go. So there's my vector 3 space. Now, like I said before, with technology these days, we can kind of do better than this, and we can think about this in a much better way. And with something like this, so now I have, so this looks kind of the same, and the red axis is my x-axis, I believe, and the green is my y, and the blue is my z. But I can drag it and kind of point anyone any direction that I want. And that's what makes it, you know, a lot more user-friendly, a lot more functional than what we've seen before. And I can add the point from the first example, and I can actually rotate and sort of visualize it in space a lot better. You can also put a floor on this if that helps. So you can kind of see relative to the x-y axis how high it is. And now I'll change it to a vector, so it's a vector to that point, as you can see. Okay. And if I do this, you can kind of see that it's gone 2 in the x and then 3 in the y. Like if I line it up to be looking at those almost two-dimensionally, then I can see what's happening there. And same thing here. I can line it up this way and see that I've gone over 3 and up 4. And of course with this you can zoom out and you can do all kinds of different things. So, you know, now it becomes much more interesting and useful to visualize things in 3 space with technology like this. Okay. Okay, so let's see a few more definitions. Remember the unit vectors. So in 3 space, the unit vectors are I hat, j hat, and k hat. Okay, and if I wanted to draw these to show them like we did before, there's my z and my y and my x. Then I hat goes out 1. So this is 1, and this is I hat. J hat goes out 1. J hat. And K hat goes up 1. Okay, and so that's sort of what they look like. Remember, a unit vector is any vector that has a magnitude of 1. The unit vectors, the standard unit vectors in 2 space or 3 space are I hat, j hat, k hat, and they're just the unit vectors that go along the axes. Okay. So if I have vector v, which is x, x, 1, y, 1, and z, 1, then that is x1, 0, 0, plus 0, y1, 0, plus 0, 0, z1, or in other words, x1 times I hat plus y1 times j hat plus z1 times k hat. And I think this probably doesn't seem all that useful to us. Like, why do we keep talking about these unit vectors? Why do we keep writing this out and showing these 3 different ways of representing a vector? Like, it's fairly simple, straightforward, but who cares? But again, we're not going to get into it enough to really see why thinking about these unit vectors is important. If this was something, if you explored linear algebra and vectors further, I'm sure that you would see why. We're just not going to see that very much. So, just take my word for it that this is a sort of just standard definitional part of it, and we're not really going to see its importance too much, and that's okay. But it is a question once in a while that's going to come up. Rewrite this in terms of the unit vectors, and so that's what it means, is to write it out like this. So it's enough for us in this course to just kind of get that that's what that's asking, and just write it out like this. We're not looking for a deeper meaning or anything. We're not going to really see that. Okay, magnitude of 3D vectors. So this one is, you might guess at what it is if you think about what the magnitude of a 2D vector is, but this almost feels like one of the ones where you would guess and you would say, there's no way that could be right. It can't be that simple, and why would that hold? But it's true that if you have vector u in 3 space, ABC, then the magnitude of u is a squared plus b squared plus c squared. And it kind of looks like Pythagorean theorem, but in 3 space. And it's surprising, but this is actually correct. And I would encourage you to explore on your own why this is true. Once it's shown, once it's pointed out why this is true, it's fairly straightforward. It's not hard. It's not a hard proof or anything like that. So it's something that you might be able to figure out yourself. I'm sure there are videos of it available online somewhere as well, or at some point, if you're curious, you can ask why this is true, and I'm happy to show you. But I'm going to leave it to you to think about, because I think that would be an interesting exercise to explore that on your own, because I think it's doable for most people. But it is just a formula, and it's nice because, again, it's just scaling up from 2 space to 3 space. And so there's not a lot of memorizing. There's not a lot of extra work or anything to do. Okay, so let's look at some examples, and we're not getting too far into it yet. These are just, I guess, specific examples of those 2 things, the unit vectors and magnitude, so pretty straightforward. Let's see. In terms of I hat, j hat, k hat, vector u is 2 I hat, because I hat is 1, 0, 0, so scalar multiplication of 2 times 1, 0, 0 would be 2, 0, 0. Plus negative 1 times j hat, so just negative j hat, minus 3k hat. So there's no reason why we have to write it out in several steps like this to show that. The point of this was to explain why this works. And if you think about scalar multiplication, and if you replace I hat, j hat, and k hat with their actual vectors, 1, 0, 0 in the case of I hat, and you actually multiplied through with the scalars and then added those three vectors together, you would get this. Like, that's the point of what is happening there, okay? So there's nothing strange about it, except for the fact that it seems bizarre to do it. But it's straightforward once you kind of get that and make sense of that. Okay, and then the magnitude is going to be the square root of 2 squared plus negative 1 squared plus negative 3 squared. And that works out to 14. Okay, and scalar multiplication is exactly what you would expect it to be. You just multiply the constant k or the scalar k through by each of the components. So again, nothing strange or new happening here. I think it's fairly obvious that that's what it would be. Now, example 3 is a bit different. Find the value of b that makes the two given vectors collinear. What does this mean? Well, it means that there's some scalar such that k times either of them, but I'm going to do it times the first one, k times 1, 2, 3 equals 5b 15. So it looks like the scalar would have to be 5, because 5 times 1 gives you 5, and 5 times 3 gives you 15. So 5 times 2 gives you 10, so obviously our answer is going to be 10, but I'm going to show this in a bit of a nicer way. But that's what it means for them to be collinear, right? That means there's some scalar that they are a scalar multiple of each other, okay? So, and what some people sometimes say, well, what if it was 1, 2, 3 and 5b 20? Well, then that's impossible, right? If you already have two components, they have to be scaled up by the same amount in order for the whole thing to work. So that would never happen where you would have, a piece of it that doesn't work or doesn't fit, doesn't make sense. Okay, but what I'm actually going to do is I'm going to make a proportion. So 1 over 5 equals 2 over b equals 3 over 15. Okay, so, and this means I've scaled each of them up because they're all equivalent fractions. And then I only need 2 of them. I can't do it with 3. So this ends up being b is equal to 2 times 5, which is 10. Okay, and it was easy to do by inspection because the numbers were friendly, but if the numbers weren't friendly, then using a proportion like this and thinking about it as a proportion is a good way of doing it. Okay, find b and c so that the two given vectors are collinear. So this is a similar example, except there's 2. So again, I'm going to do a proportion, and I get 2 over negative 3 equals negative 14 over b equals c over 12. And again, you can't solve all of this all at once, so I'm going to do it as 2 separate questions, and I get one of them to find b. I'm going to get 2 over negative 3 equals negative 14 over b, and then the other one, I'm going to get 2 over negative 3 equals c over 12, and obviously you always have to use the one that's got 2 values in it, and this means 2b equals 42. Positive 42, or I can write it out like this, and b is going to be positive 21. And in this case, negative 3c is equal to 24, 2 times 12, and so c is negative 8. Okay, and again, thinking about this, how if they're collinear, they have to be scalar multiple of each other, and so you can set them up as a proportion like this, which makes sense. So I multiplied this by negative 7, so I multiply that by negative 7, right? That's how you would scale it that way. Okay, vector addition and subtraction. Again, it's exactly what you would expect. Vector u, given these two vectors, vector u plus vector v is going to be u1 plus v1, comma u2 plus v2, comma u3 plus v3. and vector u minus vector v. I'm just subtracting the individual components. Okay, and again, I think that's exactly as you would expect. Okay, another one here. This is another thing that we've done in 2-space, so scale it up to 3-space. If I have 2 points, point P and point Q, then the vector between P and Q in the direction from P to Q is, remember what the rule is? It's always subtract backwards. So OQ minus OP. And OQ and OP, always starting at the origin, are the ones that we can define easily, right? Because OQ just becomes x, the vector x2, y2, z2. And then I subtract the vector from O to P, which is x1, y1, z1. And it becomes x2 minus x1, y2 minus y1, z2 minus z1. Right? So subtract backwards. Again, all of this probably seems obvious, but it's important to define it and say absolutely this is how it works. Adding vectors in 3-space is the same as in 2-space. So even though these are simple definitions, it's important to define them since it's the first time we're seeing them. All right, now is where we start to see some different kinds of questions where, you know, you could have a quiz or a test where you'd have a page or two of all different kinds of questions like this. A, B, C, D, E, F, G, H, I, all different kinds of questions just asking you to do different things with vectors. And they seem simple when somebody's walking you through it, but it's actually can be harder than that. Okay, so this is something to be aware of that, you know, before I show you how to do this, maybe you pause and you think about how you would do it and see if you can figure it out yourself without being shown. So from P to Q, again, I'm subtracting backwards. So it's 3 minus 2, 0 minus 5, and -4 minus -1, which is -4 plus 1, which is 1, -5, -3. Questions always come up in school. What kind of work do I have to show? With vectors, we're not super hung up on how many steps you show, that kind of thing. You know, these are all 1-mark questions. I would say a question like that's a 1-mark question. So, you know, if you went straight to the answer, I think you'd get away with it. This is a good step to show, especially now while we're learning this and thinking about it and make sure that we understand, because finding vector PQ, even how simple it is something that people forget. So, you know, you can show that step to remember what you did, I suppose, but it's not really about how many steps we show for these questions. It's really about understanding what it's being asked and being able to do it accurately. Okay, so vector PQ in terms of the unit vectors. Well, I've got PQ, it's right there. If I didn't have PQ, if it just said PQ in terms of the unit vectors, I'd have to find PQ first. But since I have PQ, I can just write it out in terms of the unit vectors. And like before, we took a few steps to do this, but now I'm just writing it out in one step, because again, it would just be a 1-mark question. Okay, and that is vector PQ in terms of the unit vectors. Magnitude of PQ, so I'm just using my formula, 1 squared plus -5 squared plus -3 squared. 1 plus 25 plus 9. Whenever you square something, it's positive, so you would always be adding in there, and that works out to root 35. Okay, so those are pretty straightforward questions, but this one's a little bit more interesting. Two unit vectors that are collinear with PQ. So if you recall when we did this before, so it's got to be collinear, it's got to be parallel, but it has to have a magnitude of 1. And so we use the k value, 1 over the magnitude of the vector, to multiply through. And that works in 3-space as well. Okay, so we already have the magnitude. So I'm just using that magnitude. If I didn't know the magnitude, I'd have to figure it out first. And that on its own, if I hadn't walked you through this and asked you to find the magnitude first, and I just said, find a unit vector collinear with PQ, it's enough for some people to go, wait a minute, I don't know how to do that, right? Oh, I have to find the magnitude, 1 over the magnitude, multiply through. But out of context, and when it's just on a test, it is surprisingly more difficult. Okay, and I'm just writing out PQ, but each of the components over root 35, which was the magnitude. But it said 2 unit vectors that are collinear with PQ. So there's one. How would I find another one? And again, this is something that you could think about yourself. Can you think of a way to come up with a second unit vector that's collinear with PQ? Okay, this is a unit vector, but that's not collinear with PQ, so that one's not going to work, right? So you can't just come up with anything. In fact, there's only one other one. And again, if you think about this, there's only ever going to be 2 unit vectors collinear with a vector, okay? Even in 3 space, even in 2 space, it's all the same. So if you notice what I've done, I've just multiplied through by -1, and I just have a unit vector that's in the opposite direction now. And those are the only 2. One that's in the same direction as PQ and one in the opposite direction of PQ. Those are the only 2. Okay, so you're never going to be asked to find 3, but if you're asked to find 2, that's how you do it. Okay. The dot product for Cartesian vectors. For Cartesian vectors in 3 space. Not just Cartesian vectors. I think we're going to sort of talk about the dot product for 3D vectors, both versions of it, right? Whether we're talking Cartesian or not. So, if you remember what it was in 2 space, then it's, again, intuitive what it would be in 3 space. So given vectors A and B, it's going to be A1 times B1 plus A2 times B2 plus A3 times B3. So you're just adding in that third dimension, components of the third dimension. Okay, or if it's not in Cartesian space, or even if it is also equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. Okay, so that's still true. That's the same formula, and the other one is basically the same, but adding the A3, B3. Okay, and again, all of this stuff that we've already done in 2 space, now we have to be able to do it in 3 space, and all the stuff that we're going to do moving forward, well, it's going to be in 3 space, but we do have to know how to do it in both. And then in the next unit, it's interesting because we flip back and forth between 2 space and 3 space, and the questions and the understanding can be different depending on what you're talking about, whether you're in 2 dimensions or 3 dimensions. And so it's again important to just have a really solid grasp of all of this. Okay, so here's a few more examples. Again, just doing different things. We're given 3 vectors here. What is -2 times c? Well, I'm just going to take -2 and multiply it through by each of those components. So it's 0, 6, positive 6, -2 times -3 is 6, and -18. Right? It's as easy as that. A plus B minus C. So so it's going to be 1 plus 2 minus 0. And then 2 plus -3, which is minus 3, minus -3, which is plus 3, and then -5, plus -1, so minus 1, minus 9, and this works out to 3, 2, -15. Okay, and there's nothing fancy here. Again, it's just getting us working with vectors and getting used to all this kinds of stuff. The magnitude of A plus B. This one is, these ones, are simple, but how do you show the work in a meaningful way? So I'm going to add A and B. So 1 plus 2, 2 plus -3, -5 plus -1. So I get 3, -1, -6. And I'm just going to write it like that. The magnitude of that vector, which is A plus B, which is equal to but it's still a vector because I've got it written in square brackets, right? So it's still a vector. If I wrote it with, if you're ever supposed to be talking about a vector and you write with round brackets, oh boy, that's a problem. Okay, we're really picky about that. So make sure you're using square brackets for vectors, round brackets for points. So that's 9 plus 1 plus 36, which is root 46. Okay. B dot C, so dot product. So that's 0 plus 9 minus 9. That's 0. Do you remember what that means in 2 space? Means the same thing in 3 space. It does mean that they are perpendicular. When the dot product is 0, they're perpendicular. Perpendicular in 3 space is a little bit more interesting than perpendicular in 2 space in some ways, but it still means that they are perpendicular. Okay. Find a vector that is orthogonal. What's that word to 2, 3, negative 4? What does that word mean? Orthogonal is just another way of saying perpendicular. It tends to be the one we choose in 3 space. You'll see it used more, but it basically you can think of it as meaning the same thing as perpendicular. It's just another way of saying that, but we tend to use that word when we're talking about vectors, and we tend to use that word in 3 space. So the word is orthogonal. Okay, how do I find a vector that's perpendicular or orthogonal to this vector? Well, there's actually a really easy trick. And again, this gets you kind of thinking about just how to manipulate vectors and how to think in the right headspace. If it's going to be orthogonal, then the dot product has to equal 0, right? That's what that means. So I'm just going to force it and I'm going to make it be 0. If I was dotting this vector with another vector, it'd be 2 times whatever the x coordinate of that is, plus 3 times whatever the y coordinate of the vector is, plus negative 4 times whatever the z coordinate of the vector would be. And it has to equal 0. So the easiest way to come up with one, and quite frankly, it's pretty easy, is pick one of these 3 brackets and stick a 0 in there. And then just make sure that these add up to 0. So they're going to add up to each other. So I'm going to multiply this one by negative 3, so I get 6 and 2. So negative 6 plus positive 6 plus 0 is 0. And therefore, the vector is negative 3, 2, 0. Right? But you could come up with other vectors fairly easily. I mean, I could scale this up or down to find other vectors that are also orthogonal. But I could also do, let's see, if I put the 0 there, then I would want to do a 4, so I get positive 12, and a 3, so I get negative 12. And that would be another one, right? And you could stick the 0 in any of those places, and you're going to get a dot product of 0. Fairly easily. Okay, I think this is the last thing we're going to do today, and this is a brand new kind of question. Determine the angle between A and B, the given vectors. So how are we going to do this? Well, we're going to use our formula for dot product. And we're going to use this one to start. Okay? And if I can figure out what the magnitude of A is and the magnitude of B is, well, that's good, because then I'm getting further to being able to isolate for theta. But I can also do A dot B because these are Cartesian vectors, I can use the Cartesian version. So what I'm going to do off to the side here is I'm going to figure out what all of these things are. So this is square root of 5 squared plus 1 squared plus negative 2 squared, which is 25 plus 1 plus 4, so root 30. And then B. Generally speaking, when you find the magnitude of something, we're going to leave it in exact. We're going to leave an exact value. And if it's reducible, you would reduce it, right? Except in this case, it's not a final answer, so there's not really any good reason to reduce it. I'm just going to be punching it into my calculator later anyway, so there's no value in that. See, I mean, it's not wrong to. We wouldn't have to, but if you go back and look at the other ones that we did before, I don't think I mentioned it, but they weren't reducible. That's why I didn't reduce them. Okay, so this is 9 plus 16, which is root 25, which is 5. That one I'm going to reduce because 5 is easier to write. And then a dot b, using the Cartesian formula, is 5 times negative 3 plus 1 times 0 plus negative 2 times 4, which is negative 15 plus 0 minus 8, which is negative 23. And now I can plug these in. I'm actually going to rewrite this first. A dot b divided by the magnitude of a and times the magnitude of b gives me the cos of theta, which is, again, as we said, by definition, the angle between them. So now I can plug in a dot b is negative 23 over 5 times root 30, and theta is inverse cos of that, which works out to 147 degrees. Again, your calculator's got to be in degrees for that. Okay. Okay. So that was the last example that we're doing for today. That was vectors in 3 space. This one here is, this example 8 is one that's important to have seen because, you know, it's fairly straightforward, but figuring it out all entirely on your own might be tricky. But once you've seen it once, it's more or less the same thing every time. And again, it just gets us working with vectors and doing all the different things we have to do, like finding their magnitudes, working with dot products, different things like that, right? So that's vectors in 3 space. Again, a lot of that is just new notation and defining the basic operations, as well as the dot product, which is the new one that we're seeing with vectors. And next, we're going to spend 2 days on the final product between vectors, which is the cross product. Cross product is only makes sense in 3 space, so that's why we had to talk about vectors in 3 space first, but it will be the final product and final operation that we'll look at. But again, a big part of this unit is just getting used to the notation on all these little different things that you have to do, finding vectors that are collinear or 2 vectors that are collinear to another given vector, doing some basic operations with them, finding magnitudes, finding dot products, possibly drawing conclusions of the dot product, like that that 2 vectors are orthogonal, something like that, okay? So that's really the big part of this unit because this notation is so new. So that's vectors in 3 space.